Let's go full screen. Alrighty. So, good morning. Welcome to Algebra 2 CP on this Wednesday morning. It is April 22nd. I hope you're all having a fantastic day. Today, what I would like to do with you, after just a little bit of an introduction, is I would like to just show you a lot of examples on graphing rational functions. I know that we did a lot of notes last time. We went over kind of the overview of rational functions, what a rational function is, what an asymptote is, why an asymptote exists, and all that fun type of stuff. So today, what I'd really like to do, once we have time, is I'd like to go ahead and just grind out some examples with you. Just show you, here's an example, here's another example, here's another example, and just keep going, as many examples as we can fit in today. A couple things I want to tell you first. Just a quick reminder that if you haven't done so already, please make sure you fill out the attendance form on Google Classroom. It's just a quick little form. It takes 2 seconds, the same one we've been doing every day, just to confirm that you are present for the day. Second thing I want to tell you is hopefully you received the email that I sent out the other day. If you did not receive it, then or if you didn't get a chance to look at it, I know you all received it. If you did not get a chance to look at it, please make sure you go back and check it out. It just describes our class structure for the fourth quarter going forward. And I want to go ahead and summarize that to you now. Definitely go back and read the whole thing because there's a lot of important information in there that should clarify any misconceptions or questions that you may have. Though if you do still have questions, you can, of course, feel free to reach out and ask. What I'd like to do, the routine I'd like to get into, is after every class period that is on a Wednesday, that takes place on a Wednesday, such as today, I will be giving you ungraded practice work to try on your own. So I will post that on Google Classroom actually right after today's class. So you have some ungraded practice work that is purely for your benefit. You don't have to turn it in, you don't have to submit it, but I do encourage you to do it because number one, the answers are provided so you can check your work easily, and number two, it is great practice for those graded assessments which will be coming to you soon. So again, after every class period that ends on a Wednesday, I am going to assign you some ungraded practice, just provide you and say, here you go, here's some ungraded practice work that you can go ahead and try. After every class that ends on a Monday, however, I am going to assign you a graded assessment, okay? As you may have heard, which is true, all assessments in the fourth quarter will be weighted equally, so you won't have the big summatives and the little PAs. Every assessment is exactly equal. And by getting into this weekly routine of having an assessment every Monday, I feel like that will, number one, give you a good amount of grades so that your fourth quarter grade is an average of a ton of things and not an average of just one or two things, which would be very bad. And also, it will get us into a nice routine that we can get used to. Oh, practice work after Wednesday's class, progress assessment after Monday's class. Any progress assessment that I assign after a Monday class period will be due on Thursday of that week at 11:59 p.m. The reason for that is just because that's plenty of time for you to go ahead and get that completed. That's like 3.5 days. Additionally, we do have a class period in that stretch of time on the Wednesday. So that's a good opportunity for you to come here and ask any questions, clarifying questions if you have any on that assessment as you're working on it. Okay, so that was sort of my logic for that. Because of the sufficient amount of time that I believe that I am providing you, that's 3.5 days to complete a progress assessment. And the progress assessments, just like the ones we've done in class and the ones that we've done via virtual learning, are not terribly long. They're like 4 or 5 problems, 6 problems max maybe. So this should take in the realm of about 30 minutes. If they're not incredibly long, I believe that is definitely a sufficient amount of time to be able to get them done. So I am not inclined at this point to accept any late assessments. Okay, so everything should be submitted by that deadline of, if it's assigned Monday after class, Thursday at 11:59 p.m. And the reason for that is so that I can then grade them on Friday and provide feedback to you. Okay, so that's the reasoning for the Thursday deadline. All right. Does anybody have any questions on any of the information either in that email or the information that I told you just now? Again, please make sure you go back and read that just to make sure. We're all A-okay on that. So again, after class on Wednesday, ungraded practice. After classes on Monday, we're going to have a graded assignment due on the following Thursday. Every week. And that should get us in a nice routine for Algebra 2 of regularly practicing and regularly keeping up with our work. So that's my logic anyway. All right, I take it by your silence that there are no questions or concerns. If you do have any, though, please feel free to type them in chat or just unmute yourself and speak up. Don't feel like you're interrupting me. Don't feel like I'm going to be mad or annoyed. I'm here to help you, so please, please, please go ahead and let me know. All right, so with that all out of the way, what I would like to get into, like I mentioned, is doing more examples of graphing rational functions. Just to recap from last time, a rational function is any function that has a variable in its denominator. We saw that the parent function of a rational was 1 over x. And having variables in the denominator can result in these weird things happening, these weird things more specifically referred to as asymptotes. Lines that your function approaches, or almost like barriers that your function approaches but never actually touches. We see that happen here and here on the x and y axis respectively with just the parent function, but we see that that vertical asymptote, the one that goes up and down, and the end behavior asymptote, the one that goes left and right, can be shifted all around based on the actual values that you see showing up in your function. Okay. Two types of asymptotes that we encountered were the vertical asymptote. The vertical asymptote is caused by the divide by zero case. So if you have a function like this, for example, your vertical asymptote would be at x equals 5 because you could not plug in 5 into this function. Because if you tried, you would be doing 5 minus 5, which is 0, 1 divided by 0, and then we're stuck, right? We would get stuck. There wouldn't be anything to do. So because of that, we need to make sure that we specify this as a vertical asymptote. That's what causes that weirdness. The end behavior asymptote is a little more complicated to do. You may remember from last time, there are a lot of notes here, that the end behavior asymptote, in order to find it, we compare the degrees of the numerator and the denominator. If the degree of the denominator is larger than the degree of the numerator, and degree, remember, refers to the value of the highest exponent to which a variable is raised. So for our little example up here, we saw that the numerator had a degree of 0 because there were no x's at all. The denominator had a degree of 1 because it's x to the first power. Therefore, it does satisfy this first case, so our end behavior asymptote would be 0 from this chunk plus the vertical shift of 3. So it comes out to be an end behavior asymptote of 3. All right. If the degree of the denominator is the same as the degree of the numerator, the end behavior asymptote comes out to be a fraction of the leading coefficient of the numerator divided by the leading coefficient of the denominator, and then plus any vertical shift that you see. So although that seems like it's complicated and scary, it's really not as bad as it looks, because consider an example like this where you have 2x over x minus 1 and then plus 3. Your end behavior asymptote would just be same degree, so it would be 2 divided by 1, the leading coefficient of 2 divided by the leading coefficient of 1, which is 2, plus 3, which makes 5. Okay, so it's nothing crazy. It's not going to be anything super complicated. We just go ahead and take those leading coefficients, divide them by each other, and then tack on that vertical shift. Alrighty? Last but most certainly not least, it could be the case, not really for us, but it could be the case in general, that the degree of the numerator is larger. If that does occur, it's what's called a slant asymptote, in which your normally perfect horizontal end behavior asymptote tilts either this way or this way, and that results in your function tilting along with it, either this way or this way. Due to the distance learning, we decided to cut that out this year, so that is something that honors only will be experiencing, but it is important that you're aware that, like, hey, this is a thing that could occur in the wide world of math. And if anybody's actually interested in learning about them, please let me know. I'd be happy to show you my office hours or any other scheduled time. All right, so after we determine the vertical asymptote and end behavior asymptote, we draw them in on the graph. It gives us nice guidelines for how to sketch our graph. Then I go ahead and test points. The way that I select points is I go 2 points to the left and 2 points to the right of your vertical asymptote. Your vertical asymptote here is at x equals 1 in this specific example. We go 2 to the left, which is -1 and 0. That's why I elected to plug in those values. And 2 to the right, which is 2 and 3. That's why I elected to plug in those values. We take them, we plug them into the function, and we get these answers, which leads to graphing these points. Right? Once you do that, you're able to draw nice smooth curves that approach but not touch the asymptotes. See right here, approach but not touch, approach but not touch. Okay? Any question? Should be a pretty comprehensive recap of what we talked about last time. Does anybody have any questions on anything to do with what we talked about last time? I'll give you a couple seconds to let that sink in. Any questions, comments, concerns about that? We're sitting, we're focusing, we're absorbing the information. Seems like we're a-okay. If If you do have anything, though, again, feel free to let me know. All right, so you may notice that I do have this sticky note here. You might be wondering why it's here. It is not just here randomly. One thing that we did not talk about last class that I do want to talk about today is the domain and range of these functions. Oh yeah, you know what's going to happen. Whenever we talk about graphs, we talk about domain and range. So not surprisingly, it comes up here. The domain and range of these functions is a little odd, because if you notice, if I asked you what's the domain of this function, you might be like, oh, well, domain is just the space that the graph occupies relative to the x-axis. So left and right, where is the graph located? Oh, well, it goes to the left forever, and it goes to the right forever. So you may be tempted to say that the domain is all real numbers. It goes to the left forever and goes to the right forever. However, it skips over this value of x equals 1. We can't plug in 1 into this function. 1 is not a valid x value. So it's like this domain has like a jump in it, right? We go from negative infinity up to 1, and then we skip over 1 and go from 1 to infinity, right? And that's exactly what our domain should look like. The domain of this function I would write as negative infinity to 1 union 1 to infinity. It's literally everything less than 1 and everything greater than 1, just not 1 itself. Does that make sense to everybody? Okay. The range is very similar in that the range goes, remember, the range is the space that the function occupies relative to the y-axis. In other words, scan vertically and see where the graph is. Well, it goes down forever, so yes, it goes to negative infinity. And yes, it goes up forever, so yes, it goes to positive infinity. But it skips over this end behavior asymptote value of 3. Do you see that? How it never actually includes 3. It includes everything less than 3 and everything bigger than 3, but just not 3. And so we'd write the range accordingly as negative infinity to 3 union 3 to infinity. Okay, it's everything less than 3 or everything greater than 3. Any questions about domain and range? You probably notice right away that, oh, domain is just really skipping over the vertical asymptote, and range is really just skipping over the end behavior asymptote. And to that I say, yes, it is. So that's a great observation. Okay, we're all happy with that. We're all satisfied. We're all feeling fine. All right, excellent. Let's start to grind out some examples now. Okay, here we go. Let's do some good examples. How about, let's get one piece of paper. I had a big stack. Let's get something like this. Ready? Good example. Okay. How about f of x is equal to, let's do 3 over x minus 4 and then plus 1. Okay, something like that. F of x is equal to 3 over x minus 4 plus 1. The first step when we're dealing with any one of these problems is we want to identify our asymptotes, starting with the vertical asymptote. Again, remember the vertical asymptote is caused by the divide by 0 case. So which value, if I plug it in for x, results in dividing by 0? It would be x equals 4, because 4 minus 4 would be 0. Likewise, we find the end behavior asymptote next. What we do is we compare the degree of the numerator and denominator. I'm just going to throw this back on here so you remember that there's 3 cases. The degree of the numerator, again, is 0 because there are no x's up there. The degree of the denominator is 1. Therefore, the degree of the denominator is larger. It satisfies this case right here, in which the end behavior asymptote is 0 from this piece and then plus our vertical shift of 1. So in our example here, my end behavior asymptote would be y equals 1. Does that make sense to everybody, how we did that? Now what I'm going to do is I'm going to go ahead and draw in my graph. Try to draw a nice, neat coordinate plane here. Something kind of like this. You probably notice I left a lot of space over here because your vertical asymptote is at 4. So I don't want to like waste a lot of paper. We know we're going to be kind of playing around in this space on the coordinate plane. So it makes a lot of sense. And our end behavior asymptote is 1 right here. A common student mistake that happens is a lot of students mix up the vertical and end behavior asymptotes. A lot of students draw our vertical asymptote at x equals 4 and draw it here. Remember that vertical goes straight up and down, so that's the one that goes through the x coordinate of 4. The end behavior asymptote, end behavior is a concept that we talked about earlier in the year, and it talks about what happens as your graph goes to the left forever and to the right forever. So that's a good way that you could remember that vertical is up and down, end behavior is left and right. All right, anyway, now that I have those in place, I'm going to go ahead and test points. Okay. Which points am I actually going to go ahead and plug in? Well, my vertical asymptote is at 4. So let's pick 2 to the left and 2 to the right so I can get a nice, accurate picture of what's going on with my function. Since my vertical asymptote's at 4, I'm going to choose 2 and 3 from the left. We'll skip over 4, and we'll do 5 and 6 from the right. Okay. Just like when we dealt with parabolas, and when we found that x-coordinate of the vertex, we went 2 to the left and 2 to the right. It's the same exact concept. When I have my vertical asymptote at 4, let's plug in 2 and 3, and let's plug in 5 and 6, just to see what's going on. I take these values now and plug them into the function and see what I get as answers. Ready? In the denominator, 2 minus 4 is negative 2. 3 divided by negative 2 is negative 1.5, plus 1 is negative 0.5. So I have a point at 2, comma, negative 0.5. Try to draw that as accurately as possible. 3 goes in. 3 minus 4 is negative 1. 3 divided by negative 1 is negative 3, plus 1 is negative 2. So I have a point at 3, comma, negative 2 right here. Let's hold off on drawing the curve until we have all our points. 5 goes in. 5 minus 4 is 1. 3 divided by 1 is 3, plus 1 is 4. Point at 5, comma, 1, 2, 3, 4. 6 goes in. 6 minus 4 is 2. 3 divided by 2 is 1.5, plus 1 is 2.5. So I got 6, comma, 1, 2 and a half. All right. Notice the symmetry that you should see between these types of things, right? These appear to be about the same distance away as these appear to be about the same distance away from that center cross-section of the asymptotes. That's absolutely true and is a good indicator that you're graphing these correctly. So now I'm just going to go ahead and draw my curves that approach but don't touch the asymptotes. Approach, but don't touch the asymptotes, just like that. Okay. Notice how they're not right angles, they're not hard corners. It's a nice smooth curve. Okay. Any questions, comments, concerns about that? The last thing, of course, that we have to do is we got to talk domain and range. Can't do a graph and not talk domain and range. Just like we saw when I was going through the previous example, the domain goes left to right, but excludes the vertical asymptote because we can't plug in 4. So it's everything less than 4 and everything greater than 4. I would say that it's a negative infinity to 4, union 4 to infinity. Range, same deal. It goes down forever, it goes up forever, but it excludes this value of 1. It's everything less than 1, negative infinity to 1, and everything greater than 1. Notice that I'm using the parentheses instead of the square brackets because it does not include 1. Okay. Any questions about that example? That's a nice, straightforward example. Okay, let's do another one. How about something like this? F of x is equal to, let's do 2x over x minus 1 and then minus 4. Okay, something like that. Nice rational function. Has a variable in the denominator. Let's give it a shot. First of all, my vertical asymptote. My vertical asymptote is whatever x value causes us to divide by 0. It would clearly be 1 in this case because 1 minus 1 is 0, and that's bad. That's why it causes the asymptote, because it's bad. So I'd say my vertical asymptote is x equals, it's gross. I don't want anything to do with that. Like, why would I even bother plugging in 1? It's just going to result in dividing by 0. Don't do that. It's an asymptote. Next, we find our end behavior asymptote. What I do is I compare the degree of the numerator and denominator and then tack on my vertical shift. So the degree of the numerator, if you notice, is 1 because it's x to the first power now. There's an x up there. The degree of the denominator is also 1 because we have an x to the first power. A lot of students make a common mistake of saying that the numerator would have a degree of 2. That is not the case. Remember, degree refers to the exponent. The leading coefficient is 2. That's absolutely true. But the degree of the numerator is just 1. So I have the same degree in the top and the bottom. When I have the same degree in the top and the bottom, bringing this back in here, right here, I want to go ahead and take the leading coefficient of the top divided by the leading coefficient of the bottom and tack on the vertical shift. Leading coefficient of 2 divided by leading coefficient of 1. 2 divided by 1 is 2. Minus 4 is negative 2. Okay. Does everybody understand and see, hopefully, why the the end behavior asymptote is -2? Awesome. Fantastic. All right, now let's go ahead and actually test some points. Okay. Oh, and actually sketch our graph. Sorry, I have to also sketch my graph. Let's see. Graph. Kind of looks a little like this. Now I have my vertical asymptote at x equals 1. Draw that in. My end behavior asymptote at y equals -2. Probably should have left a little more space down at the bottom here. There we go, something like that. Okay, now let's test some points. Again, since my vertical asymptote is at the x-coordinate of 1, I want to plug in a couple values on the left and a couple values on the right. My x-coordinate is 1, so I'm going to go ahead and plug in -1 and 0. I'm also going to go ahead and plug in 2 and 3, right? That's 2 to the left, 2 to the right. So I'm going to plug in -1, 0. I'm also going to plug in 2 and 3. Okay. Does everybody understand why we're picking those values? Just counting. It's just counting 2 to the left and counting 2 to the right, and that's all there is to it. All right, so now that I know those, I'm going to go ahead and take these and plug them in and see what I get. -1 goes in. -1, sometimes when you have, by the way, a plug-in on the top and a plug-in on the bottom, it's a little easier to write it out so you don't get confused and don't forget the previous results that you got. So if I take -1 and plug it in the denominator, -1 minus 1 is -2. In the numerator, 2 times -1 is also -2, and then -4. So I have -2 divided by -2 is 1, minus 4 is -3. Everybody see that? So I have a point at -1, comma -3 right here. Okay. Now I can go ahead and plug in 0. In the denominator, 0 minus 1 is -1. In the numerator, 2 times 0 is 0. Then -4. 0 divided by -1 is 0, and then -4 is -4. So I got a point at 0 right here, comma -1, 2, 3, 4. Again, just seeing those 2 points there, you should be able to visualize this curve that's going to be approaching but not touching the asymptotes here. Now I go ahead and do the other side. I take 2, I plug it in. We'll do the numerator first this time. In the numerator, 2 times 2 is 4. In the denominator, 2 minus 1 is 1. And then -4. That's easy. 4 divided by 1 is 4. Minus 4 is 0. So I got a point at 2, 0 right here. And then 3 goes in. In the numerator, 2 times 3 is 6. In the denominator, 3 minus 1 is 2. And then -4. 6 divided by 2 is 3. 3 minus 4 is -1. Bingo, right there. All right, see that symmetry that shows up in the graph? That's a great indication that you are doing the problem correctly. Now I can go ahead and draw in my curves that approach but don't touch, approach but don't touch the asymptotes, just like that. Okay. The last thing, of course, we have to talk about is domain and range. I never want to forget that. The domain is everything to the right and everything to the left and everything to the right of 1, just not 1 itself. So it's -infinity to 1, union 1 to infinity. It goes to the left forever, but stops at 1, goes to the right forever from 1, right? It just jumps over that 1 value. Same thing with the range. It goes to the bottom, it goes down forever, it goes up forever, but it does not hit this value of -2. -infinity to -2, union -2 to infinity. Alrighty. Any questions, comments, concerns about that at all? Everybody's processing, everybody's thinking. All right, fantastic. All right, let's go through just one more. I think that's all we have time for is one more example. Okay. How about something like this? We got x minus 4 divided by x minus 3, and then plus 5, just like that. First thing I'm going to do again, it's a rational function. I see that x in the denominator, so we have to identify what the asymptotes are. The vertical asymptote here is x equals 3. The end behavior asymptote, and the reason why it's x equals 3, by the way, is because 3 minus 3 would result in dividing by 0. But dividing by 0 is bad. The end behavior asymptote, let's compare the degree of the numerator, degree of the denominator. The degree of the numerator, if you notice, is 1 because it's x to the first power. The degree of the denominator is also 1, x to the first power is the biggest you see. Therefore, it satisfies our second case in which the degrees are the same. When the degrees are the same, we make a fraction out of the leading coefficient at the top, leading coefficient at the bottom, and then tack on the vertical shift. So take a look. 1, which is the leading coefficient, divided by 1 is 1, plus 5 gives us the end behavior asymptote of y equals 6. Okay? Does everybody see why that's the case? Okay. Now I can go ahead and sketch my graph. I'm going to leave a lot of room up at the top there because, again, we notice that my end behavior asymptote's at 6, so I'm going to be like working up in this space, so I want to make sure I leave a lot of space for that. I have my end behavior asymptote at y equals 6, 3, 4, 5, 6. My vertical asymptote was at x equals 3, 1, 2, 3, right here. Now I can go ahead and test some points. Just like before, I want to do 2 to the left and 2 to the right of the vertical asymptote. So my vertical asymptote is positioned at x equals 3. 2 to the left, we have 1 and 2. 2 to the right, we have 4 and 5. So I'm going to go ahead and plug in 1, plug in 2, plug in 4, plug in 5. Everybody see that? Hopefully everybody's understanding again why I'm selecting those values in particular. Okay. Again, the vertical asymptote's at 3. I'm just selecting 2 to the left and 2 to the right. Let's go ahead and take these and plug them in. Again, with an x in the top and in the bottom, when you have a variable in the numerator and in the denominator, it's a little easier sometimes to write it out as opposed to doing it all in your head. So if I go and take 1 and plug it in the numerator, 1 minus 4 is negative 3. In the denominator, 1 minus 3 is negative 2, and then plus 5. So I have negative 3 divided by negative 2 is positive 1.5, plus 5 is positive 6.5. So it looks like I got a point at 1 comma 6.5. That's 1, 2, 3, 4, 5, 6 and a half. Okay. I take 2, I plug it in. In the numerator, 2 minus 4 is negative 2. In the denominator, 2 minus 3 is negative 1, and then plus 5. Negative 2 divided by negative 1 is positive 2. Plus 5 is positive 7. So there's 1, 2, 3, 4, 5, 6, 7. Bam, right there. Everybody sees how we get those values, hopefully. Let's do the other side. Again, but before we even do the other side, you should be able to see, like, can you picture the curve and what it's going to look like? Approaching but not touching the asymptotes. That's why we draw in those asymptotes, because they serve as those nice handy guidelines. I take 4, I plug it in. In the numerator, 4 minus 4 is 0. In the denominator, 4 minus 3 is 1. Plus 5. 0 divided by 1 is 0. Plus 5 is 5. 1, 2, 3, 4, 5 right here. 5 goes in. 5 minus 4 in the numerator is 1. In the denominator, 5 minus 3 is 2. Plus 5. I have 1/2 plus 5, which is 5.5, or 5.5. So that should be right about there. If my asymptotes were drawn a little more accurately, you would see that it would be equidistant from these points. They should be symmetrical from each other. So now I see curves that approach but don't touch the asymptotes. You see them and you draw them in just like that. Curves that approach but don't touch the asymptotes. And that's a nice accurate graph of what that should look like. Again, we identify our domain and range just to cap things off here. What is the domain of that function? It's all real numbers to the left, all real numbers to the right, just not including x equals 3. So I'm going to say it's negative infinity to 3, union 3 to infinity, everything to the left of 3, everything to the right of 3. And our range goes down forever, goes up forever, but does not include 6, negative infinity to 6, union 6 to infinity. Okay? And that, my friends, is that. Any questions on anything involving these rational functions that we've talked about today? Please feel free to ask. While you're thinking of questions, let me just remind you that there is going to be some practice work posted on Google Classroom. I'll do it right at the end of this class. It is to your benefit to complete that. It's not graded or anything, but do make sure you get that done. You can feel free to stop by my office hours at any time to ask me questions about it as well. Next class, what we're going to do is we're going to explore just some more examples of rational functions. Just want to keep showing you a couple more examples. But at the end of next class, we are going to have our first progress assessment of the fourth quarter. It will be assigned at the end of next class, and it will be due by Thursday night. Okay, I think that's, again, a generous amount of time. If you do have any questions or concerns, please feel free to reach out. Other than that, that's all I have for you today. I hope you have a fantastic rest of your Wednesday, and I will see you on Monday. Have a great weekend, and again, reach out if you have any questions. Miss Mal is going to type up the notes too, or write out the notes, and they're going to look great. She's going to upload them. She's been doing a great job. So go ahead and check out those notes, and again, have a fantastic day. Oh, and go to our office hour session if you want to do that too.